Could everybody please have a seat? Tonight, I'm delighted that we have another university professor speaking to us, Dr. Ed Cackett from Wayne State University. He obtained his doctorate from the University of St. Andrews in Scotland, where his thesis concerned matter interacting with black holes and neutron stars, which I understand is still an area that he's very actively researching. After his doctorate, he was a postdoctoral fellow at the University of Michigan for 4 years. Then he traveled back to England, to the University of Cambridge, where he spent a year and a half at their Institute of Astronomy. Then in January 2012, he came back again to Michigan, to Wayne State University, where he's an assistant professor. His topic tonight is Neutron Stars, Humanity in a Sugar Cube. Dr. Cackett.
Okay, so as Dale said, my sort of main area of interest and research has always been neutron stars and black holes. Everyone's seen the movies and heard all about black holes, and neutron stars often get sort of short-shrifted. Yet, I think neutron stars are just as exciting and just as extreme, almost as extreme as black holes. And so I want to tell you about neutron stars today. And the talk is entitled Humanity in a Sugar Cube, because as I'll tell you, these stars have densities that are equivalent to crushing the entire human race down into the side of a sugar cube. And so one of the interesting things about studying neutron stars is trying to figure out what happens if you crush the entirety of the human race down to the side of the sugar cube. So the story about neutron stars starts in 1932 with the discovery of the neutron. This chap, James Chadwick, was working on understanding the atom at the time, and he was doing some experiments trying to figure out what the atom was composed of. And in 1932 he discovered neutron and completed our sort of basic picture of the atom, where here we have the very center of the atom, which is made up of neutrons and protons, and then we have our electrons around the outside. So the neutrons are these neutral subatomic particles, protons are positively charged subatomic particles, and the electrons are negatively charged. So in the center, we have the neutrons and the protons. I'd like to show this. This is actually the full article of his discovery of the neutron. Right? This is taken from the journal Nature, published in 1932. These 6 paragraphs about the most beautifully succinct and concise paragraphs you read about a Nobel Prize winning discovery, right? So you get a Nobel Prize for writing 6 paragraphs. And he discovered the neutron basically through simple physics, right? Conservation of energy and conservation of momentum, right? So these are relatively simple high school principles, or high school level principles that he used to discover this particle and won the Nobel Prize for. Okay, that's 1932. Anyone want to take a guess at how long it took for someone to come up with the idea that you could make a star entirely of neutrons? Anyone have a good idea? 1880s? 1990s? No? Anyone see? Sorry?
A little sooner.
A little sooner than the 90s, yeah. It was just 2 years later, 1932.
Sweet.
These 2 guys, right? Many people recognize Mickey, right?
Yeah. Mickey, that's right.
Fritz Mickey, you'll know, is famous for this the discovery of dark matter, right?
Right.
He was looking at the velocities of galaxies and figured that galaxies in clusters were traveling too fast, so there must be this mysterious matter there that gives extra gravity. But he was working with Walter Baade at the time, 1932, on supernova explosions, so the explosion of a star at the end of its lifetime. And they came up with the idea that in this explosion, you may actually be able to form a star made entirely of neutrons. And the sort of idea goes something like this. You have the core of your star made up of mostly iron. When you stop nuclear fusion, your fuel source turns off, the core of the star collapses. And under the collapse, you get extreme energies and extreme densities. Now, those densities are so high that it causes all the atoms to break up. So the atoms break up into their constituent parts, neutrons, protons, and electrons. And when you get to a high enough density, you can even force those protons and electrons to join together and form neutrons. So you go from having a star made up of atoms to having a star made up of almost only neutrons. Right? So the idea is you have a star made of neutrons left over from the explosion of a large star at the end of its life. I'm sure you're all very familiar with what a supernova random looks like, right? This is the Crammed Nebula, so I'm sure you all know. And it's one of my favorites, supernova 1006.
Yeah.
And so it's a natural place to try and look at neutrons. Okay. Neutrons discovered in 1932. Neutron stars suggested in 1934. Anyone want to guess now when they were discovered?
67.
67, yeah, good. Someone knows their history. Good.
Right, the Pulsar thing.
Yeah, Pulsars, 1967. Pulsars were discovered. We already heard a bit about the history of the telescope tonight. And this is the Martin Ryle's telescope array at the University of Cambridge. Jocelyn Bell here was a graduate student in the 1960s working with Anthony Hewish. And she was studying radio signals from quasars, right? So quasars are quasi-stellar radio sources. They were discovered in the late 50s, and they were the in thing to study in the 1960s, right? And so she was working on looking at these things and trying to understand what they are. We now know that quasars are supermassive black holes at the centers of galaxies. Right? At the time, no one knew what they were, and so she was just studying bright radio sources in the sky. And she found an object that had a recurring signal, right? A periodic signal, every 1.337 seconds. So this is what it looked like. Here's the brightness as a function of time, and she saw a blip occurring occurring periodically every 1.337 seconds. Didn't know what this was, right? Why would you be seeing something that's periodic in the sky only about a second, right? And so they nicknamed it Little Green Men 1, LGM1, right? They didn't know what this was. They quickly found several more, and so they ruled out that this was actually from Little Green Men. And they were able to figure out that this thing was coming from our own galaxy. And it now has the name PSR for Pulsar B1919 plus 20, the coordinates of where that object is in the sky. And here is the paper where they discovered, or the abstract of the paper where they discovered this observation of a rapidly pulsating radio source. And they say, unusual signals from pulsating radio sources have been recorded at the Mullard Radio Astronomy Observatory. The radiation seems to come from local objects within the galaxy and may be associated with oscillations of white dwarf or neutron stars. So they figured out very quickly after the discovery that to have something with a pulse period of only 1.337 seconds, it's got to be small, right? And the smallest known stars are white dwarfs and neutron stars. Neutron stars have actually basically been forgotten, right? So Baade and Zwicky come up with this idea in the mid-30s, and people had essentially ignored it and forgotten about it until this discovery was made in the 60s. Controversially, the Nobel Prize was given to Anthony Jewish and Martin Ryle, and not to Jocelyn Bell, who actually herself had made the discovery. So, the smoking gun of this being a neutron star was they went and looked at the Crab Nebula, and they saw that there was a pulsar at the center of the Crab Nebula. And so they go, okay, yes, the idea is that we form these things from in the supernova explosion. We go and look in our best known supernova remnant and we find a pulsar at the center, right? So these things are most likely neutron stars. So why are these things giving us these recurring signals? Well, the idea is that there's something like a lighthouse. You have a star, and it has beams of radiation coming out either end of it. Essentially what's happening is that the extremely strong magnetic fields accelerate the particles, and they get shot out into space down its magnetic axis. This is its magnetic north pole and magnetic south pole. You get these beams of radiation coming out either end. Now, its magnetic pole is misaligned with its rotational axis, right? In the same way that the North Pole and the magnetic North Pole on Earth are misaligned, right? Here we have our magnetic North Pole and our rotational axis misaligned. And so this means that as the star rotates around, those beams of radiation rotate around too, right? So every time this rotates around, it's like a lighthouse beam, and if we're looking at it just right, that beam will come right in front of our eyes and we'll see a pulse every time that beam of radiation comes around as the star spins around. And so the idea is that 1.337 seconds that she was measuring in that first pulsar is actually the time it takes that star to rotate one time around. Okay, so...
Question?
Yeah, sure.
Why wouldn't it be that it rotated half the time around in that time? Wouldn't you get a
because it has to be pointing directly at us. If you think about, if we have an observer over here, right, if this rotates around, we'll only see it once. We'll never see the south, the magnetic south.
Gotcha.
Right.
That's true.
And we discovered one where we happen to be edge on with the magnetic pole?
We have to be. The only way to be able to see
In other words,
the
have we ever seen one where, and could you tell the difference between you're seeing just the North Pole, for example, or you're seeing the North and the South?
Oh, could you see both the north and the south? Yes, you could, but I'm not sure whether any have been found like that. I don't know. It's a good question.
Could be right on the beam.
You have to be right on
Right on the equator, yeah.
You have to be off by 90
And
degrees.
the axis of rotation would have to be absolutely perpendicular to our point of view.
Not in our lifetime.
Okay, so let me
In other words, not yet.
run through a few key facts about neutron stars. So their mass is about 1.5 times the mass of the Sun, and that's crammed into a star that's just 10 to 15 kilometers in radius, right? So that's like cramming the Sun into something not much bigger than the size of Detroit, right? So, as I said in the title of my talk, that's the equivalent of cramming the human race into a sugar cube, and it means that the very center of these stars have densities that are about 10 times more dense than an atomic nucleus. Right? And so, material in neutron stars is the densest directly observable matter in the universe. I have the word directly observable in there, of course, because black holes clearly have more dense than neutron stars, but they're not directly observable. We actually see light coming from neutron stars, right? And so these are the densest directly observable matter in the universe.
Question.
Yeah,
How can they be 10 times more dense than an atomic nuclei?
because they don't have atomic nuclei. I'll explain. Don't worry. Okay, let me run through a few more facts about neutron stars. I have sort of a list of properties. Every property you can think of in a neutron star is extreme. Okay. Its magnetic field, about 1 trillion times the magnetic field of the Earth. Its surface gravity, about 100 billion G. Gravity on a neutron star is so high The escape velocity is something like 0.3 times the speed of light. The gravity is so strong that you see 70% of the surface at one time, right? You actually see light that comes from the back of the star. The gravity is so strong that it bends the light, and so you actually see light that is actually initially going away from us gets bent around into our line of sight. Right? So you actually see more than half the star because the gravity is so strong. And they spin fast. 1.337 seconds is nothing for a neutron star. The fastest neutron stars rotate about 700 times a second. Right? So this is a star, the mass of the sun, or a little bit bigger than the mass of the sun, the size of the city, rotating 700 times a second. So, you can ask the question, why do the stars rotate so quickly? The answer is actually relatively simple, and it's from a principle called conservation of angular momentum. Right? You're probably all familiar with the idea of an ice skater spinning around, and if they have their arms out, they spin slowly, and if they move their arms in, they go fast. If you're not familiar with this, you've probably all been bored in your office at some point, sitting on a spinny chair. You've spun around, you put your arms and legs out, and you know you go faster than you pull them in. Right? If you haven't done that, you clearly have an extremely interesting job. And that's a principle called conservation of angular momentum. Things that are bigger will rotate slower. If you make things smaller, it will start rotating faster. Okay. The core of the star that ends up being the neutron star is way, way bigger than the neutron star is when you only end up with, right? So just by conservation of angular momentum, you find that the neutron star has to spin up when it collapses down to something so small. Okay, what are neutron stars made of? That kind of seems like an odd question, right? I've told you these are neutron stars, right? They're made of neutrons, right? Well, that's only half the story. They're actually a little more detailed than that. And they're kind of cool. They have a structure that's not so different than the sort of picture of the structure of the Earth. Densities are just a bit different. Yeah. The neutron stars have an atmosphere. The atmosphere is probably something like a centimetre thick. Typically, it's made of only hydrogen. Anything heavier than hydrogen settles very, very quickly. Beneath that, we can have an ocean. That ocean is of heavy nuclei, which sits on top of a solid surface. These are the only type of stars to have a solid surface. Right? That crust is maybe a kilometre or so thick, and it's made of iron nuclei, typically. Why do you get a crust? Essentially, those nuclei get pushed so close together, the density is so high, that you end up getting forced into a very structured shape, and they form a lattice structure like salt. This is a sodium chloride body-centered cubic lattice structure. You actually form very similar structure when you have the huge densities on the surface of the neutron star. These things get forced to be in a very sort of regular shape. Think about ball bearings in a jar, right? If you push them all down, right, they form in a very sort of regular pattern in the jar, right? So you have a solid surface, about a kilometre thick. You can even have mountains on your neutron star, actually. The highest mountains are probably of the order of millimetres high, and you would not have enough energy in your entire lifetime to climb to the top of the mountain of the neutron star, simply because the gravity is so high. As you go down into your neutron star, the density gets higher and higher and higher. And you get to this transition region between the crust and what we call the outer core. This is where things start to go funny, right? Nuclei get into densities now that they don't want to be nuclei anymore. Nuclei actually start to get stretched. We actually get a layer that we call the pasta layer. And we call it the pasta layer because you can get a whole bunch of funky shapes. So you can get spaghetti-shaped nuclei. You can get penne-shaped nuclei, right? You know, the long ones with the hole in the middle, right? You can even get Swiss cheese type sort of shape, so things with holes, regular holes. And that's just an effect of the densities being strong and stretching this nuclei out of shape. As you go deeper and deeper, the nuclei can no longer stand this, and they get split apart. Right? So no longer have an atomic nucleus. You end up with your neutrons, protons, and electrons, a sort of sea of neutrons, protons, and electrons. As you go deeper and deeper, the densities get higher and higher and keep on ramping up. And you force these protons and electrons to be very, very close together. And that actually causes them to collide, and you get them creating neutrons. And so as you go deeper and deeper into your neutron star, you get more and more neutrons. And then you get to the inner 1 kilometer, we call the inner core. And we have a question mark, because physics, the physics that explains this, which is called quantum chromodynamics, is a beautiful theory, but we can't calculate the densities of these sorts of sensitive stars. So we don't actually know what is in the center of a neutron star. Simplest thing, it could just be neutrons, right? But it could be way, way more complicated than that, or more interesting than that. You could have particles like kaons or pions. It could even be not a neutron star at all. You could actually have a quark star, right? So you could have, instead of having the neutrons in the center, the neutrons themselves are actually made of particles. Neutrons are made up of 3 quarks, 1 up quark and 2 down quarks. And it could be that the neutrons break up and leave you with just 3 quarks. And so instead of actually them being neutron stars, they could actually be quark stars or strange quark stars. So one of the things about studying neutron stars, we actually want to know what's at the center. What happens to material when you crush it to greater than 10 times nuclear density? Do you end up with neutrons or something else? How would we go about trying to do this? What you have to do is you actually have to try and measure the radius of the star. Why do we want to measure the radius of the star? Because basically, you want to know, how big the star is, because if you have quarks in the center, they can actually get a little bit closer to each other than neutrons can. And so your quark star would likely be about 8 kilometers in radius, where a neutron star would be something like 10 kilometers in radius. So if you can measure the radius of your neutron star, something like an accuracy of 0.1 kilometers or better, right? You would actually be able to start distinguishing between the sort of weird things you can have at the center of a neutron star. And so I'm going to try and tell you about how we go about measuring the radius of a neutron star. I'll talk about one specific way. There are probably 10 different ways of trying to measure neutron star radii. The hope is we'll get the same answer from these 10 different independent methods, and you can verify then that the answer you're getting is really right, and you can have a good idea of what's going on.
Sir?
Yeah,
What temperature are these stars?
I'll get to that in a bit. Okay, so just to give you an idea of how hard it is to try and measure the radius of a neutron star, it's the equivalent of having a DNA helix on the moon and observing it from Earth and being able to measure the size of that DNA helix, or the width of the DNA helix. So that's if you put a 10-kilometer star at the sort of typical distances in the galaxy that we see now. Okay, so where do we see neutron stars? We need to try and pick a good way to see neutron stars. Well, if you look anywhere across the electromagnetic spectrum, you actually see neutron stars. They were obviously discovered as pulsars and radio waves. They're well known and visible, and I'll mostly talk today about in the X-rays. And why when I talk about them being in the X-rays will become apparent in just a few minutes. Okay, so where do we see neutron stars? Well, the obvious place to look, of course, is in supernova remnants, right? You know there's been an explosion. You know that a neutron star could be left at the center. So here's the Crown Nebula again. The explosion was in 1054 AD. So the neutron star at the center is going to be about 1,000 years old, less than 1,000 years old. very young in astronomical terms. You look at X-rays at the very center, this is what you see. You see a neutron star, and you see a whole bunch of hot gas spinning around. You can see jets of material being shot out either side of the neutron star. Just to give you an idea of how the optical region and the X-ray region compare. In red is the optical region, in blue is this X-ray nebula in the center, right? So we have the neutron star, the hot, what we call the pulsar wind nebula, and you can see these are beautiful, but these are really complicated. If you want to try and measure neutron star radius, this is not the place to do it, right? All that hot gas makes things much more complicated, makes it hard to use these objects.
How many light years is the Crammed Nebula from here?
I don't know, I'm afraid. Yeah. You guys probably know the distances like that much better than I do.
I tell you, it's
In the app, get the app.
Okay, here is to show you the stuff that's going on at the center of the Crammed Nebula. This is about 10 images stitched together from the Chandra X-ray telescope. They're taken over a period of about 10 years, and you can see how, again, you can see how this is a really dynamic region, right? Stuff is happening in this region, and if you really wanted to try and study the neutron star itself, this would be a really complicated place to do.
6,523 light years.
There you go, that's your answer. Okay, where may be a better place to study neutron stars? Where I look is in these objects called X-ray binaries. You may recognize this image. I spotted it on the way in, right? If you haven't noticed, if you've gone the way out, look at all the Cranbrook Space Odyssey posters. They've all got this image on it. This is an X-ray binary system. This is a star like our sun, orbiting around a neutron star at the center. And what's happened is it's evolved to the point where the material is transferring from the sun-like star across to the neutron star. And you form a disk of gas and dust spiraling in down to the neutron star. The gravity of neutron stars flowing in, as this stuff falls in, it's giving up gravitational potential energy and converting it into kinetic energy and heat. And so this gets extremely hot. And so it gets so hot that the thermal emission from this disk of gas, this accretion disk we call it, is emitting thermally in the X-ray part of the spectrum. And so if you were to look at the X-ray sky, the brightest things you see in our galaxy are all X-ray binary systems. They're all the objects where material is falling down onto a neutron star or a black hole. So these are actually remarkably easy to find, right? SCO-X1 that was mentioned earlier today, the first X-ray source, extra solar X-ray source, is a neutron star X-ray binary system. Okay, so we can look at X-ray binary systems, we can use them to try and measure neutron star radius. How do we end up getting the radius? Well, actually, one of the ways I'm going to talk about is basically the same method that you use to get the radius of any star. It's just a little more extreme when you talk about neutron stars. You use the fact that the neutron star surface is going to be emitting thermally. And you can use the properties of that thermal radiation to try and measure the radius of the neutron star. Everything that's hot emits radiation, and the wavelength of that radiation just depends on the temperature, right? So here is some humans, and we have a body temperature of 98.6 degrees Fahrenheit, and so we emit thermal radiation in the infrared part of the spectrum, right? That's how these night vision cameras work, right? They just look for thermal radiation in the infrared part of the spectrum. The sun, our nearest star, photosphere is at 6,000 degrees, so it radiates in the visible part of the spectrum. It peaks in about green, okay? Our neutron stars, the ones in our X-ray binary systems, their temperature on the surface is a few million degrees Kelvin, and so their thermal emission is now in the X-ray part of the spectrum. Right? So if you look at X-rays, you can actually measure the temperature of a neutron star surface. But how does that help us get the radius? Well, the property of thermal radiation is that its brightness depends on the temperature that it is, the size that it is, and its distance. We know the temperature. We can measure the temperature from looking at the X-rays. So if we can know its distance, we can figure out how big it is. Why does this work? Well, you know that the further away an object is, the fainter it gets. So a candle in this room is clearly easily visible. If I was to go 10 blocks away, you'd have a hard time seeing it. The bigger an object is, the brighter it gets. If instead I replace that candle 10 blocks away with a bonfire, you'd absolutely have no problem seeing it, right? So, obviously, a star, the further away it is, the fainter it gets. But the bigger the star is, the more light it emits, right? So, if we can measure the distance to our star, and we can get its temperature from looking at its X-ray properties, we can end up getting its radius. And so that's the simplest way of measuring a neutron star radius. It's actually the same way we would go to measure about the radius of many other types of stars. Okay, so how do you go about observing X-rays? Well, the problem with observing X-rays is that blasted atmosphere stops them getting to the surface. While that's actually great for life, you know, if the atmosphere wasn't there, right, we'd all have skin cancer pretty quick. It makes it really hard for us X-ray astronomers, and we have to launch our satellites, we have to launch our telescopes into space to be able to observe X-rays. The two major ones in space at the moment are NASA's crammed Space Telescope and European Space Agency's X-Men Mutant Space Telescope. I also work with Japanese Space Agency's Suzaku Space Telescope. These two were both launched in 1999 and are still going splendidly, doing very, very well.
Is New Star good for this sort of thing?
New Star looks at hard X-rays, so it looks at typically higher energy X-rays than these look at. These go up to an energy of 10 kilo-electron volts. New Star typically looks from about 5 to 70 or so. So it's it looks at high energy X-rays essentially. Okay, so how do you go about observing X-rays? Of course, when you say X-rays to people, the first thing anyone thinks about, of course, is an image something like this, right? And so the immediate property you know about X-rays is that X-rays pass through things, right? And they pass through things easily, right? So then you have this problem. How do I focus my X-rays, right? I want to build a telescope. I want to focus the X-rays onto a detector to get an image, right? Or to collect the light. But my X-rays are going to pass through whatever mirror I build, right? So I can't use the same setup as I would for an optical telescope. Here's the telescope you're all familiar with. The light comes in, passes up the primary mirror, passes up the secondary mirror, and goes into your eye, right? X-rays just go straight through this, right? No good. Have to think of something different, okay? And so you have to build your X-ray telescope slightly different. This is how the Chandra X-ray telescope looks. It uses these things here, these shells, are its mirrors, right? The X-rays come in across from here, and they bounce off the mirror here, they bounce off the mirror there, and they go down to the detector. They basically come in almost parallel to the mirror, right? They come in very, very close to being parallel, and they just sort of graze off the mirror. That's how you end up, the only way you can actually reflect these X-rays. In Chandra, these shells are made of glass, and they're coated in gold and iridium. So you can imagine the cost of building these things. And the way that you make your collecting area bigger, rather than just making a bigger mirror like you would with your optical telescope, you just add extra shells, right? You're just going to keep on adding more and more shells. So the more shells you put on, the more collecting area you have. You're limited by two things. One, as you go further out with your shells, you change the focal length of each of those mirrors, right? And the other one is weight, and that's actually the biggest problem. You have to fit these things into a rocket. In fact, Chandra was actually launched on a space shuttle, so you have stringent weight requirements. And so it turns out that weight limits how big you can build these telescopes. Distance between these mirrors and the detector is about 10 meters. The detectors at the end, CCD cameras, so they're not so different from the cameras you have in your smartphones. They block out optical light and they're sensitive to X-rays. Okay, so we have these X-ray telescopes. We can use them to collect X-rays from neutron stars, and we can figure out then, we can try and use this to figure out how big the neutron stars are. So, what do we find? Our best measurements so far give the rays of neutron stars still between about 10 and 13 kilometers. And the accuracy so far is not good enough to be able to distinguish between different possible types of things you can have at the center, right? Whether it's a neutron star or whether it's a quark star. But we're working on it. We're trying to do better. This is one of the best measurements so far. This is mass as a function of radius of the star. And this sort of area here is what's sort of allowed. So anything between sort of 10 and 13 kilometers, you can see. Stuff over here is ruled out, stuff over here is ruled out. This is the sort of allowed region. How are we going to do better? We need bigger, better telescopes. And how are we going to do that? Well, there's actually interesting things coming along in just next year. Well, this should say 2016 now, actually. ASTRO-H is a joint Japanese and NASA X-ray mission that's going to be launched at the beginning of 2016. It just changed the launch date a few months ago. And it's going to have the highest energy resolution ever. So it's going to be able to know the energy of every X-ray that hits the detector better than any previous mission. And what that's going to do is give us a few extra different types of ways of being able to measure neutron star radius. Another interesting project is called NISA. This stands for Neutron Star Interior Composition Explorer. And it's going to be launched, and it's going to be on the International Space Station. This is the International Space Station. It has these places on the outside of it. You can mount scientific equipment, right? And NISA is going to sit on one of these arms, and it's going to be able to view a large fraction of the sky. It has a good collecting area, and it's going to be able to very accurately time X-rays that arrive at the detector. And so it's actually going to try and use X-ray pulses to try and measure the radius of neutron stars. So, hopefully, if I come back in 3 years' time or 4 years' time, when this stuff has come through, we'll have a much better answer for what the size of a neutron star is. And we may have a better answer to knowing whether we have neutron stars at the center, or whether we neutrons at the center, or whether we have quarks at the center, or whether it's something completely different that we haven't thought of yet. Okay, with that, I'll stop and I'll take questions. Thank you.
Hypotheses now, or even horseback guesses of what percentages would be quark versus neutron?
So I would say there's only one true, what we call equation of state for a neutron star, which would mean that you can't have both quark stars and neutron stars. You can only have one type of matter, right, at those densities. So we should find either quark stars or neutron stars. You won't be able to find both, because essentially the idea is that when you crush matter that dense, there's only one thing it can become, right? Either quarks or neutron stars. I would say the best guess so far is probably that it's not quark stars. The reason being that there was a neutron star discovered a few years ago that has a mass of 2 solar masses. It's the heaviest neutron star found yet. That likely rules out most of the models for quark stars. There are some models still allowed, but they're looking less likely than they were, I'd say, 5 years ago.
Fine.
There was something on the spin of the discovery of the neutron star where it was pulling gas from the other star. And of course, we know that that would produce a supernova in the white one. Would it be the same thing when the pulsar gets too much stuff again, or does it just...
So, theoretically, if you could make your neutron star go above the maximum mass of a neutron star, which is probably somewhere between 2 and 3 solar masses, it would collapse to form a black hole. But these objects have companion stars about a solar mass. The neutron star is probably around about 1.4 solar masses. So you have to eat up the entire star to be able to do that. And that won't happen, right? Because at some point, mass transfer between the 2 stars will stop because the matter will come across, and then the star no longer fills its own gravitational sphere of influence. And so the matter will no longer transfer between the 2 stars. And so you'll get a small star, maybe half a solar mass, and a neutron star orbiting around each other without mass transfer between the 2. And so the likelihood is you'd never transfer enough mass across the neutron star to make it go supernova.
Even if the companion is really massive to begin with?
If you had a high mass star, which you can have, right? You can have high mass stars that have neutron stars, but then the problem is that the high mass star has a very short lifetime. And so you would never have a long enough time for you to transfer enough matter across for that star then to be able to go above the...
If it was high enough mass, it would beat the neutron star becoming a neutron star.
Yeah, right. Who had their hand up first?
This is talking about supernova stars. Now, how about a star that just goes nova like this one in the teapot? I guess, I'm assuming that would not create a neutron star. Can that create something all by its own nature, or?
So that if you have a nova, it's just an explosion on the surface of a white dwarf, right? The white dwarf stays a white dwarf. Only when you push that white dwarf over 1.4 solar masses will it then go supernova and form a neutron star.
Hypothetically, I'm the crystallographer at Wayne State University,
Okay.
so I'm always thinking in terms of crystals.
Sure.
Hypothetically, if you could wait long enough till the universe cooled down long enough, isn't it possible that you could consider a neutron star, the core of a neutron star, simply a conglomerate or ordered lattice of neutrons in cubic or hexagonal closest packing?
No, to the density. So the core of a white dwarf is certainly that, right? It's a crystalline structure, right? The surface of the neutron star is the crystalline structure, but the densities are too high inside the neutron star for it to ever do that. It's melted essentially, right? You're above the melting point. You're above the melting temperature and density, or pressure, or whatever you want to say. You're above the melting pressure and temperature for that material. So it's always going to be fluid.
Even after a couple year of cooling.
Yeah, because gravity can go away, right? Gravity is the thing that's really creating the pressure, right? And it's the pressure that's, I mean, it's not just temperature that melts things, it's pressure too. It's the combination of both of those things.
The difference in the density of a neutron star that's spinning faster than a slow one?
Is there a difference in the density? Not very much. The reason being that the neutron star crust is probably the strongest material in the universe, one of the strongest materials in the universe. And so the star doesn't change much in size when it's rotating. The maximum sort of rotation rate for a neutron star, theoretically before it would break up, it's probably about twice what's been observed. Right? So they're not that close to break up, but it's really changing the shape of the neutron star.
So the only way we can detect a neutron star is if there's something orbiting around it and getting pulled down so it can emanate this radiation, this X-rays. Is that true?
That's the easiest way. In the supernova remnants, I mean, it's also an easy way to find them. They're not always in binary systems. Pulsars are usually actually single stars on their own. And there's also a class called isolated neutron stars, which were discovered at the nearby neutron stars that have been discovered through their thermal X-ray emission.
So they're still hot.
They're still hot. They're a few 100,000 years old, probably. And they're still hot from their formation. They haven't cooled down yet. So
But they'll eventually cool down.
they'll eventually cool down to close to zero, right? I mean,
And it basically become dark objects. You wouldn't be, it'd be like black holes. You wouldn't be able to detect them because unless there was something, being sucked down into them and, emitting radiation from that.
yeah, but the time scale for a neutron star to cool really cold is longer than the edge of the universe.
Will the
So-
spin stop, is what the question is?
Will the spin stop? Yeah, eventually they'll slow down. They have magnetic field is actually slowing the spin of a neutron star. You can actually spin up neutron stars too, right? So neutron stars in binary systems, that material falls onto the neutron star. It's like if you're having a basketball on your finger spinning, right? It's like you're tapping the basketball to make it spin faster, right? And so that material comes in and it hits the star, it spins the star up. So you can actually, they do slow down, but they can also spin up.
With a billion G surface, things that hit the neutron star hit really hard.
Yeah, they're actually spinning material that hits the neutron star surface, actually traveling faster than the rotation speed of the neutron star, which gives you interesting effects between the material and the surface of the star.
So
You
what's
get
the
some weird layer between the two.
What's the ultimate state of the neutron star?
In what way?
How does it end? Or what's your way?
It will, it will just keep on cooling down. It will slow down and cool down and become a black star, black neutron star, whatever you want to
Actually, on that, so a black hole, through Hawking radiation will eventually evaporate. There's nothing like that for neutron stars.
Now, and black holes, you hear that said all the time, that black holes will evaporate through Hawking radiation. If you do the calculations, the time scale for 10 solar mass black holes evaporate through Hawking radiation is many times the age of the universe. Right? So black holes aren't going anywhere. And the supermassive black holes in the sense of galaxies certainly aren't going anywhere.
At the moment, they're not actually net evaporating because the cosmic microwave background is enough photons to keep them going.
I was just wondering that image that you had of the X-ray emission from the craft. I'm not really sure if I'm interpreting it right, but it looks to me like you could infer from that the rotation axis and the magnetic field axis are aligned for the craft.
They are misaligned, right? I think. I think the image is hard to tell exactly what's going on because you're not really resolving anything, right? The very center of it, remember the neutron star is 10 kilometers, right? So, you're not even getting close to resolving that, right? So what you're really seeing is a whole bunch of hot gas around it, right?
Can we go back?
Yeah, let me show you. So this is the magnetic axis this way, where the jets are coming out. I would say it's hard to tell which way that's rotating, right? This is so much bigger than. Yeah, I think your eye can tell you whatever, right?
And how many
it's
years
also
is that?
completely undersampled, right? This is 10 observations over 10 years or something like that, right? It's actually rotating once a second or something, right? So you're not getting even close to seeing what the rotation is.
Yeah, it's like using a strobe light on a spinning object. You
Yeah.
make it look like it's going backwards.
Watching it as fast as you would.
So when these things, when their spin slows down, where does angular momentum go?
It gets lost through magnetic energy. So the magnetic field is able to transfer particles away from the star, right? And so you actually get really accurate.
What about gravity waves?
You also get gravity waves from these things, right?
Slow down.
So to get back to the end question, what if it is a quark star, what happens when it cools down?
That's a good question. I mean, quark stars themselves also can have a crust, right? The cool thing about the quark star is that the crust would not actually touch the quark material. It would levitate through electrostatic repulsion, right? And so you could actually get a thin layer of space between the core of the quark material and the crust, which would be your normal matter. Right? What would happen to the material? Presumably, it would just cool too, I think.
Okay. So never the quarks would never.
No, I don't think so. I just think they kept the density that would keep them as quarks. Yeah.
If you were to work backwards, and if you knew, you could measure, guesstimate the size of the supernova or the star, and then you know the known speed that it's rotating at, can you go from that deduce backwards to the size of the original star? Just like, like you said, if you're spinning right, you bring your arms in, you go faster.
So if you if you use the basic models for how big you think the core of a star is, and you can actually measure sort of, the rotation rates of stars that sort of size. Calculations work, right? If you do the simple calculation of if I just collapse it to this size, do I get approximately the right answer? The answer is yes, right? Can you do that to accurately figure out the size of a neutron star or figure out the size of the core? The answer is no, because these things are incredibly complicated. The guys at Los Alamos National Lab, people do use supercomputers to figure out, do calculations of nuclear bombs, right? They use their codes, or the public versions of their codes, to try and simulate neutron stars exploding, or the supernovas, right? They can't get it to work just right. I mean, it's that complicated. So it's not that well understood exactly how everything works in a supernova explosion.
One more short question. I'm sure I read somewhere, I can't remember where, spinning neutron stars make for the best clocks in the universe. Is that right?
Yeah, that's right. They're more accurate than atomic clocks. You can measure their spin down, the rate of change of their period. It's very, very small, and they are the best clocks in the universe.
We do have clocks that will not gain or lose a second in the age of the universe at the moment.
Okay, well then they are not quite the best clocks in the universe.
Certainly the best natural clocks.
Second best.
If you continue to add mass to a neutron star, at what point does it transition to a black hole, or what kind of a process would that be?
If you could transfer enough matter to the neutron star, it would probably do a supernova type explosion, like the white dwarf would do. Whether you can ever transfer enough matter is one of the questions we talked about earlier. The mass limit for the maximum mass of the neutron star is guessed at being something like 2.5 or 3 times the mass of the sun. The maximum measured mass for a neutron star is 2 solar masses, so it's certainly greater than 2 solar masses. And the collapse would be expected to be very similar to sort of the white dwarf becoming type 1a supernova, but it would be the neutron star collapsing and becoming a black hole.
Yeah, I'm curious about the magnetic field of these neutron stars. There's no electrons or anything like that. How is this magnetic? Do neutrons in themselves are they capable of producing a magnetic field?
You have electrons and protons in the star, right? But the magnetic field is actually conserved in the collapse. The same way angular momentum is conserved in the collapse of the star. magnetic field also gets conserved. And you get extremely complicated things called get magnetic flux tubes and vortices that run through the star. Right? The details of which are hideously complicated. But you essentially, it's essentially a conservation process as well.
And it retains the field.
Why it retains the field.
Also, wouldn't the stuff that's circling around the accretion disk help to generate a magnetic field as well?
That has a magnetic field, but it's not on the same order. It's not even close to the same strength as a magnetic field of a neutron star. Yeah.
I thought that neutron stars are equally bright all over.
That's a good question. Depends. So if you have a strong enough, there's a balance between. So in these stars, right? There's these branches. As the material falls down, there's a balance between the rate at which stuff falls down to the neutron star and the strength of the magnetic field. Right? If the material is coming down at a huge rate, it completely overpowers the magnetic field, it just lands on the surface, right? And it will basically equally cover the surface very quickly. If, however, it's slightly lower rate, or the magnetic field is slightly stronger, what happens is the material gets channeled down the magnetic field. It sort of flows down onto the magnetic poles, a bit like an aurora, right? Stuff happens to the poles, right? So the stuff is coming in, flows down, you end up getting hot spots on the surface. So when you have an X-ray pulsar, the X-ray pulsar is essentially hot spots on the surface as it rotates around. You could have nuclear fusion happen on the surface of a neutron star. When you're accreting material onto the surface, you could get to the critical point where you get helium or carbon detonation. Right? You get a very rapid burst. That probably starts in one location, but it will very quickly spread across the entire star.
I think we should thank our speaker here.